Okay, this is Dr. Brown. This is a very short video. We're going to talk about Hopital's rule. And this is a method of finding limits that if we had known about this and could do derivatives at the first part of this course, we could have saved a lot of time and calculated limits much easier. Now, over here on the right, there is a picture of the mathematician Hopital, who was from France, and he did this back probably in the 17th, 18th century. I could go look it up, but basically Hopital's rule says that if you have two functions, f of x and g of x, and if the limit of f of x as x approaches c equals the limit of g of x as x approaches c, and they are both 0 or they are both plus or minus infinity, and you can calculate the limit of f prime of x divided by g prime of x as x approaches c, and it exists, and if the limit of g prime of x is not 0 for all x in an interval with x not equal to c, then the limit of f of x over g of x as x approaches c equals the limit of the derivative of f of x divided by the derivative of g of x as x approaches c. Now, this is a very powerful rule, and it just simply means if you first take the limit of f of x and g of x and get 0 over 0 or infinity over infinity, that you then just go ahead and look at the limit of f prime of x, take the derivative of f and the derivative of g, and try to calculate the limit, and if that exists and equals some L, then you've calculated the limit. But you always have to have either 0 over 0 or infinity over infinity before you can take the derivatives. Now, before we get too far into this, you guys probably remember the limit of sine of x over x as x approaches 0. Notice that if you just plug in, you get 0 over 0, which is undefined, but if you were to realize that that satisfies Hopital's rule, that we could take the limit as x approaches 0 of the derivative of sine of x, which is cosine of x, divided by the derivative of x, which is 1. And notice this is cosine of 0, which is equal to 1. And of course we already knew that this limit was going to be 1, but this turns out to be a very easy way of doing it in many, many cases. Now, let's do some examples. If you look at example A here, if you plug in, you get 0 minus 0 over 0. And so Hopital's rule applies. So now we take the derivative of the numerator, which is 3, minus cosine of x. The derivative of the denominator is 1. And now plugging in, we get 3 minus cosine of x over 1, which is 3 minus cosine of 0 over 1, which is equal to 2. So the limit of this function is equal to 2. Now let's look at the limit of the square root of 1 plus x minus 1 divided by x. Notice if you plug in, you get 1 minus 1 over 0, which is 0 over 0. So Hopital's rule applies, so we have to calculate the derivative of the numerator and the denominator, and we would rewrite to find d dx of the square root of 1 plus x would be d dx of 1 plus x to the 1/2, which is, as you know, 1/2 1 plus x to the minus 1/2, which is 1 over 2 square roots of 1 plus x. So the derivative of the numerator is 1 over 2 square roots of 1 plus x. The derivative of the denominator is simply 1. Now plug in x equals 0 and you get 1/2, and that is the limit. You can try this using various other methods and you would get the same thing, but this is by far the fastest way to do it. Now let's look at some other examples. If you take the limit of this function, plug in x equals 0, you get 1 minus 0 divided by 0, which is 0 over 0. So we'll use Hopital's rule. You'll remember that the derivative of the square root of 1 plus x is equal to 1 over 2 square roots of 1 plus x minus 1/2 divided by the derivative of x squared, which is 2x. And now we need to take the derivative again, because notice if we plug in x equals 0, we get 1 over 2 minus 1 over 2 divided by 0 equals 0 over 0. So now we need to try it one more time. So we need to take the derivative of 1 over 2 square roots of 1 plus x. So I would write that as 1/2 1 plus x to the minus 1/2 power. So d dx of that is minus 1/4 1 plus x to the minus 3/2. So we now have the limit as x approaches 0 of the derivative of the numerator, which is minus 1/4 1 plus x to the minus 3/2. Of course, the derivative of minus 1/2 is 0, and the derivative of 2x is 2. Now we plug in and we just get minus 1/4 over 2, which is minus 1/8. So the limit is minus 1/8. Now, problem D here, if we plug in, we get 0 minus 0 over 0, which is 0 over 0. And now we try to use Hopital's rule, and we get the limit as x approaches 0. The derivative of x minus sine of x happens to be 1 minus cosine of x divided by 3x squared. Now we plug in, and notice we get 0 over 0 again. So we'll try Hopital's rule again. And we take the derivative, and we get the derivative 1 is 0. The derivative of minus cosine x is sine of x. The derivative of 3x squared is 6x. Now plug in, and of course you get 0 over 0 again, so you're about to give up. But let's try one more time, and we get the limit as x approaches 0. The derivative of sine of x is cosine of x. Derivative of 6x is 6. Now plug in, and we get that the limit is 1/6. Now let's look at limits as x approaches 0 from the right of sine of x over x squared. Plugging in, we get 0 over 0. We try Hopital's rule, and we get the limit of cosine of x divided by 2x. And notice cosine of x is approaching 1, but as x approaches 0 from the right, the denominator becomes very small in a positive way, so this becomes infinity, plus infinity. Now let's say what happens when x approaches 0 from the left. We're going to get roughly the same thing, except x is going to 0 from the left. Take the derivative, we get cosine x over 2x. This is approaching 1 as x approaches 0, but x is approaching 0 from the left, so it's very negative, or very small negative, like going to minus 0.00000001. So this is going to approach minus infinity. Now the last two examples, we're letting x go to infinity, and notice the limit of ln of x as x goes to infinity is infinity, and the limit of 2 square roots of x as x approaches infinity is infinity. So we got infinity over infinity, and so L'Hopital's rule applies. And so we take the derivative, the limit of x approaches infinity of the derivative of the numerator, which is 1 over x, and the derivative of 2x to the 1/2 is going to be 2 times 1/2 x to the minus 1/2, which is equal to 1 over the square root of x. And after you divide, you get limit as x approaches infinity of 1 over the square root of x, which is equal to 0. Now, the last problem we're going to look at is the limit of e to the x over x squared as x approaches infinity. Notice the numerator is going to infinity, the denominator is going to infinity, and the question is, which is going to infinity faster and overcoming the other? L'Hopital's rule will help us see this. If we apply L'Hopital's rule for the first time, the derivative of e to the x is e to the x. The derivative of x squared is 2x. And we still get infinity over infinity. So we will try it one more time. Limit as x goes to infinity of e to the x. The derivative of that is e to the x. Derivative of 2x is 2. And notice e to the x over 2 as x goes to infinity is equal to infinity. And that is a quick look at L'Hopital's rule.